Okay, so here's the last recording for this chapter. I start off talking about critical points, so critical temperature, critical pressure. So what is this critical point? So if you see in the first window here, we have a gas and a liquid, and then if the temperature is below the critical point, you have two phases, and then eventually you get to the critical temperature, and there's one phase. Uh, it's easier to explain using a liquid. The reason why a liquid hangs out is because there's an attraction between the molecules, and they just kind of hang out together in general proximity. Uh, so uh, as this excites up, you can get to a certain temperature where the molecules are moving so fast, there's so much kinetic energy that it just can't that the liquid can't stay together. I mean, of course, that is also that's the vaporization. But if you take that liquid and you push it together, so it actually has kind of a density that it could be close to that of a liquid. So it's kind of like a liquid, kind of like a gas, but it's kind of neither because there's just so much energy there, and then it's compressed to a certain point that it's got the molecules are hanging out together in a certain fashion, and the properties change. So the other thing with a critical point, properties change. So for instance, solubility changes. So nonpolar things can start to mix with polar things in above the critical point. So you can get rid of things like caffeine. So that's how you can get rid of. That's one of the ways that decaffeination happens. Critical CO2 or critical water. You can use it to extract certain things like I said, the caffeine from things. So that's critical point. Now let me talk about heating curves. So let's look at this figure here. Let me start at the bottom left corner. The y-axis is temperature. The x-axis is the heat added. So imagine you take an ice cube from your freezer and you put it on your stove in a sealed container, and you turn on the heat. This is going to happen. The ice cube is going to absorb heat. It's start going to be cold, and that's going to get to 0 degrees Celsius. That's the melting point, and then the ice is going to melt. So that's point two is the melting, and this is an equilibrium process, meaning it's some of it's melting, some of it's freezing, but eventually with the added heat, all of it melts away. Now you have liquid water. Now you heat up the liquid water. Heating up the liquid water just raises the temperature until it gets to the boiling point. That's part four. Again, we have the dynamic equilibrium, and then you get to the steam. And if you keep on adding heat to the steam, then the it just increases, and the steam gets more and more energetic. So let's talk about point number 5 there on the chart, the steam. If the steam is at 100 degrees Celsius, that is known as saturated or wet steam. Uh, and what does it mean by saturated or wet steam? It means if you touch it, it condenses. So if you put your hand in wet steam, if you're boiling water, that's wet steam, and you put your hand over it, and then water condenses on your hand. Then if you go beyond that, that's known as superheated steam or dry steam. That's known as dry steam because if it hits you, it doesn't condense. And dry steam, superheated steam, is very dangerous. So because if it gets you, you can vaporize parts of your body and cauterize the wounds instantaneously. So dry steam is used in power plants and in Navy propulsion vessels. So they use dry steam typically to turn turbines and use that for propulsion and to propulsion for ships or to drive a generator in an electrical plant. So or the propulsion system, like I said, in a Navy vessel. So when there's the superheated steam, the dry steam, that can be very dangerous for individuals. Okay, so let's go down and talk about the heat flow. So for the solid ice down in the bottom left corner, the temperature changes by the Q, the heat, equals the heat capacity times the change in temperature. And the heat capacity can also be written as the mass times the specific heat capacity. So, and the heat capacity is different for, or typically it's different for the the solid, liquid, and vapor phases. Okay, so then at point number 2, the melting point, the energy in this is just the number of moles times the heat of fusion. We talked about heat of vaporization before. Heat of fusion is the same thing. Point number 3, so the heating of the liquid water in this curve. This is the same thing as 1. The heat flow is equal to the mass times the specific heat capacity times the change in temperature. And point 4 is similar to point 2. There's a number of moles times the heat of vaporization. And point 5 is just like 3 and 1. This is the heat flow is equal to the mass times specific heat times the change in temperature, or the heat capacity times the change in temperature. So whatever is given to you is typically the specific heat capacity and the amount. So and written here is the number of moles. So this is partially correct. When you cool, so this is heating things up. So let's go the other way around. Let's say you have temperature and you're cooling things down. So if you have a liquid, so this is a liquid, and you're cooling it down, you can get a little point like this, and you can get this point here. That is known as a super cold liquid. So you can get a liquid that's actually below the melting point for a little bit, and it's thermodynamically unstable, and it's known as a super cold liquid. So you can see that happening. Another thing is when you heat things up. So let's go back to heating. Typically, it can look like this, where it's not a flat. It's actually a slope. It's actually a slope. Okay, that's an ugly line, but you can actually get a line. You can see here there's some concavity in this. This has to do with different crystal faces. So if you have a perfect crystal, it'll be just like point 2. It'll be a block. So a perfect crystal will look like that. So as I draw on here in red, it's the very blocky kind of thing. So a perfect crystal will do that way, but not everything is a perfect crystal. You have what are known as amorphous solids, and then the parts that are under high stress, so those will melt first, and then the ones that are relatively low energy, low stress, they will melt last. So you will get kind of these curves, and then you also get a range there. So that's that's how most things will actually melt. So you get a curve rather than a box. If you have a perfect crystal, it'll be a box. Everything else is going to be a curve. But that's above and beyond this class. So for this class, of course, you'll assume it'll be similar to a perfect crystal. The next thing we're going to talk about are phase diagrams. So this is the phase diagram for water. This is water here is a weird substance. Water is weird because for the most common part of water, you see here the liquid, this line moves this way. In orange right here, that's how most other substances go. So, okay, let's talk about this chart. The y-axis not drawn to scale is pressure, and the x-axis not drawn to scale is temperature. And you have a couple features. So notice right here, you have what's known as a triple point. Triple point is where you have all 3 phases, solid, liquid, gas, and equilibrium. So let me start over here at the left corner. So underneath the triple point, lower temperature, lower pressure than the triple point, you do not have a liquid phase. So there's a solid and gas. So when solids go to gases, this is known as sublimation. When a gas goes to a solid, that's known as deposition. So why do I care? That happens in your freezer. So if you not necessarily this temperature, but if you ever notice, like if you buy like a bunch of frozen peas and you stick them in the freezer, or some meat, you stick it in the freezer, and then you have it in a bag, and then later on you look at the bag, and then there's frost outside of the bag, and the meat is all shriveled up, or the peas are all shriveled up. What's happening? The ice is the water, the ice is subliming out of the bag and then depositing outside of whatever it is you have in the freezer. So that's if you're wondering why does that happen there. And so the triple point. Let me go back to the triple point. You have the liquid phase. When liquid goes to vapor, that's known as boiling. When vapor goes to liquid, that's known as condensation. Solids, when solid goes to liquids, that's known as melting. When the solid goes from the liquid goes to solid, that's known as freezing. And also notice we have the supercritical fluid, we have the critical point, that's the critical pressure, critical temperature, talked about before. If you look at this here, it says this 760 torr and it moves over. That is known as an isobar. So a same barometric pressure, isobar are a same pressure. And so if you start at atmospheric pressure and you move over, you can see that you will have all three states of matter there. So solid, liquid, gas. And then the 0 degrees and 100 degrees on the graph, they have the vertical lines. Those are known as isotherms. So iso is same, therm, temperature, same temperature. So those are some isotherms there. Okay, so let's look at water a little bit more. Water is really weird. Water is a strange compound that we have. Alpha ice or ice 1, that's the most common one that we come across. But if you increase the pressure, you can form different types of ice. And one of the things they say, and alpha ice is really weird because it floats. It's less dense than the liquid. So, but that's really weird. That's not typically what happens for states of matter. And you say, oh, there's no ice in the bottom of the ocean. Well, it turns out there is a lot of ice in the bottom of the ocean. There is ice in a different form. So with enough pressure, the different types of ices will form. Not only that, we have methane gas trapped in that, and those are known as the methane hydrates. So if you're worried about the Earth running out of hydrocarbons anytime soon, we are not even close. The methane hydrates is a ridiculous amount of hydrocarbons sitting there. So that's water. That's weird. Water is weird. We'll talk about how water is weird later. Okay, so let's talk about some other things here. So here is iodine on the left and carbon dioxide on the right. So we have the isotherm, isobar, as we said before. But you can see here that the curves are different. Water's one goes this way, but these ones go the proper way. And then there's carbon dioxide. Notice that they have the triple point at about 5 atmospheres. I've seen the triple point of carbon dioxide. It's really weird. Carbon dioxide is white, so or the dry ice is white, and the liquid is clear. So imagine white chunks sunk in a clear liquid that's boiling. That's what the triple point is. You have all three states together. So it's really weird. But at 1 atmosphere, carbon dioxide sublimes. So that's why we call it dry ice. It's cold, and it hits off the carbon dioxide fumes. It's really fun to play kind of hockey with it because the fumes kind of give it something. So you can take that and you can use it as like a hockey puck, and then we did that in grad school. We would run around and play that. So fun times, of course. So but let's talk about water. Water is a very strange compound. So ice is slippery. So surprising things you learn in chemistry class. So ice is slippery, but it's really weird that ice is slippery. What they used to think the reason why ice is slippery is because of the phase diagram looking like this, that the pressure here could actually melt the water. What really is going on though is that ice is slippery when it's close to the melting point. And if you've ever lived somewhere cold, I used to live in Wisconsin, and when it gets to be -30 outside, ice is not slippery. It's like walking on granite rock. So when it's really cold, ice is not slippery. Only when ice is close to the melting point, then it gets really slippery. But cold temperature, oh, I hated living in Wisconsin. Those -30 degrees, those are cold days. Yeah, but ice is not slippery. And the there's a thin liquid layer on ice, and that liquid layer depends on the temperature. So close to freezing, it's a relatively thick liquid layer, and then as it gets colder, that liquid layer decreases, eventually goes away. So that's the real reason why ice is slippery. Water is also an extremely powerful greenhouse gas. So, for instance, Mars has about 20 times as much carbon dioxide as the Earth does in its atmosphere, but the difference between day and night in Mars is about 60 degrees Celsius. Compared to the moon has no atmosphere. The difference is about 300 degrees Celsius. So, uh, the but the Earth, though, so the moon is well, the Earth, its average temperature is about 15 degrees Celsius, and depending on when you're out of the Earth, it has the day-night cycle, the temperature change. It depends on how much water vapor you have, and so that shows you how powerful greenhouse gas water is. So if you've ever been to a desert where there's relatively little water vapor in the air, the difference between day and night is quite large. Whereas if you're in a very humid place, the difference between day and night is not so significant. So that shows you, and that is, water is the greenhouse gas of the Earth. If it wasn't for water, the Earth would be significantly cooler than it is now. Water also has a relatively high heat capacity. It doesn't have the highest heat capacity. So like ethylene glycol antifreeze has a higher heat capacity, but it has a relatively high heat capacity. What is heat capacity? If you've forgotten, a low heat capacity means a little bit of energy will cause a large change in temperature. High heat capacity means a lot of energy causes a low change in temperature. So water is that in the high heat capacity range. Water is a great solvent, so it's especially for polar things, and it transports nutrients and toxins very well. So that's a problem with it. So it doesn't pick and choose. It transports everything, the good things and the bad things. Also, I mentioned this before. The common solid near standard temperature and pressure, the alpha ice, ice one, it's less dense than the liquid. So usually when you see a solid and a liquid, the solid is more dense and it sinks. So it's the water is the weird thing here. You think it's so common, ice floats, right? Everything should float. So if you can take olive oil. So if you take olive oil and you put it in your fridge, the longer chained acids will start to freeze first, and you can see frozen olive oil on the bottom of olive oil, and the solids will sink in olive oil. So that's an interesting thing. So if you ever want to try that experiment at home, I remember I asked my dad about that. My dad's a chemist. He would put his olive oil in the fridge, and I was asking, why is a solid sinking in that? And because ice floats, and he's my dad's like, well, son, it has to do with the properties of water, and he explained it to me. I'm like, okay, so, well, that's my childhood for you. Hey, so yeah, it's what happens when you get raised by two chemists. So okay, we're done with this chapter, and we can go on to the next chapter.